Greetings everyone, welcome to the next video in my lecture series on applied differential equations. So this video is going to be about solving homogeneous linear systems of linear DEs with complex eigenvalues. So it's the same idea as having two distinct real eigenvalues, but with your lambdas being alpha plus or minus beta I. Let me try to write that better. Lambda is equal to alpha plus or minus beta I. And what that means, remember that if you've got a matrix that has real entries, then the eigenvalues, if they're complex, come in pairs of complex conjugates. So we've basically got a lambda 1 is equal to alpha plus beta I, and our lambda 2 is equal to alpha minus beta I, where the lambda 2 is the complex conjugate of lambda 1, and in fact these are complex conjugates of each other. Now a useful thing to note here is that lambda 1 plus lambda 2, if I add those two together, then the beta i's cancel each other out. That gives us just 2 lambda, and that's real. And if I do lambda 1 minus lambda 2, I'm going to get the alphas are going to cancel, and I'm going to get 2 beta I, which is pure imaginary. And let's set that aside for later. And let's say that lambda 1 has eigenvector k1, and lambda 2 has eigenvector k2, where, again, these are conjugates of each other, and we're just going to write that k2 is the complex conjugate of k1, vector k1. And, you know, like you could, if you totally insist, you could just say that then x vector capital X is equal to c1 vector k1 e to the lambda 1t plus c2 k2 e to the lambda 2t, where we could call this whole thing, where we've got complex numbers everywhere. And, you know, that would be okay. I mean, it certainly is rigorous. It answers the question. But let us say that that's not going to work so well necessarily if we want to actually try to understand what that is doing in real space. Let's call this Z1, and this whole thing is Z2. Oops, that's 2. Okay, so let's try something else. So instead, we're going to use similar arguments to the ones that we used for second order linear DEs. With constant coefficients. You'll recall that rather than having e to the ITs and stuff like that, we ended up with e to the alpha x onto a linear combo of sine beta t and cos beta t instead, which worked out a lot better. So in a very similar way, we say if our vector k, 1 for example, is equal to a combination of a real vector and an imaginary vector. So this whole part is the real part, this whole part is the imaginary part, where b2 itself has only real components, but multiplying by I makes it into the imaginary part. Then if we take a look up above and look once again at here our z1, this entire thing here, then we can write z1. Oops, let's try writing actually using a pen. Then z1 is equal to, instead of just k now, we have vector b1 plus I b2 onto e to the, now it would be lambda 1t, and we're replacing the lambda by alpha plus beta I times t. Is equal to b1 plus I b2, where b1 and b2 are vectors. And then I'm just going to rewrite this as e to the alpha t and then e to the beta it, just using a nice little property of exponents here. And I'm going to pull the e to the alpha t out front. I'm actually going to move the equal sign a bit to the left to give me a bit more room. I've got e to the alpha t onto b1 plus I b2. And now I'm going to take the b to the it and use that nice little Euler's identity that says that e to the I times beta t is equal to cosine of beta t plus I sine beta t. That useful little formula. And so basically you can see here that we've partitioned this, so we've got real parts and imaginary parts. And then we're going to let x1, that should be a capital X1, equal, oh, and I should have a vector sign on top of that. It's going to be the real part of z1 is equal to e to the alpha t onto b1 cos beta t. Plus, now notice that if you actually take the two imaginary parts together and you FOILed this out, then you'd get also -1, you get I squared, so -1 times b2 sine beta t. So basically what we're doing is, if you were to take this expression for z1, let's put the z1 right here, and take a look at this expression for z1. Oh, I should have a vector sign on top of those too. What do you know? And you FOIL this out, then you're going to get two terms that are real and two terms that are imaginary. This should be a negative sign here. Wow, just really tired today. It's been a pretty long week. And if you let x2 then equal the imaginary part of z1, it's equal to e to the alpha t onto beta 1, b1. The imaginary part is when the b1 multiplies by the imaginary part of sine beta t. And the other imaginary part is when you take the I b2 and you multiply it onto the cos beta t. Let's remind ourselves of what we said before. Z1 plus Z2, if you were to write out Z1 from and Z2 from above, is real, and Z1 minus Z2 is imaginary. And so the solution vectors capital X1 vector and capital X2 vector can be written as X1 is equal to e to the alpha t onto B1 cos beta t minus B2 sine beta t, where capital B1 and B2 are both vectors, and X2 is equal to e to the alpha t onto B1 sine beta t plus B2 vector cos beta t. And this is very reminiscent of looking at the second order solutions for complex. We had e to the alpha x onto c1 sine cos x plus c2 sine x. So this looks, beta x. This looks very, very familiar. And where b1 is the real part of k1 and b2 is the imaginary part of k1. Okay, so in my next lecture video, I'm going to do an example of this, and I hope to see you there.